So everybody has joined. Is that the case or? Okay. Okay. So यहाँ तक समझ में आ गया होगा आई होप ना. तो यहाँ पे लीडिंग केस ही लेते हैं. So you just remember this particular step. Okay. And this is how we write. If you have, so for example, I'll give you the example. Okay, I'll write an example and then you will be able to understand. So for example, more often you will find this particular thing is written directly as a property in books or somewhere wherever you might have studied. But let us understand ये हो क्या रहा है, what is happening. Okay. Okay. So ओके. सो देखो इस फंक्शन के अंदर क्या हो रहा है. फॉर एग्जांपल इफ नाउ कंसीडर दिस पर्टिकुलर थिंग एज अ फंक्शन ओनली. सो इफ आई हैव रिटन Dirac of gx is equals to summation over I, where i's are the number of root, Dirac of x minus xi's divided by g dash xi ka mod. Okay, so this is one. ओके, दिस इज वन थिंग. अब देखो थोड़ा ध्यान से देखते हैं. एक्स स्क्वायर माइनस ए स्क्वायर इज इक्वल टू 0 करके देखो. ऑलवेज रिमेंबर कि जब भी Dirac डेल्टा फंक्शन से डील कर रहे हो, व्हेनेवर यू आर डीलिंग विद द Dirac डेल्टा फंक्शन, all you have to see is where the argument is 0. So this make it as a habit, because every time there is a Dirac delta function, try to understand ये है कहाँ. So for example, you can clearly see that this Dirac delta function has the argument of this Dirac delta function has roots at x equal to plus minus a, and both of them are simple zeros. So there are two roots. One I will write xi as a, another xi I'll write as minus a. So now this will be I Dirac of x minus xi divided by g dash xi ka mod. Now what would be g dash xi? So gx is x square minus a square, and g dash x is equals to twice x. So if you are writing g dash either plus a or minus a, this is either twice a or either minus twice a. If I want to write the modulus of it, it will become 2 times modulus of a. So what it will become? So the denominator will become 2 times modulus of a, and the first I is let's say xi is let's say minus a. So this will become x plus a, then plus Dirac of x minus. So this proves your property. So, if you have seen this property somewhere, this is how it is written. Is that clear?
Yes, sir.
Okay. Now, just try to do another question for me. Just try to find an integral that I'm giving to you. So this is an integral that I'm giving to you as a question, so that now class becomes certainly interesting. So minus infinite to infinite, if I'm giving you this integral, e to the power minus modulus of x, Dirac of sin x. What will be the value of this particular integral? So what will be the value of this particular integral? Let us first find. Okay, so first you should define where your Dirac is like where the roots of sin x lie. So I will write simply here. यहाँ पे लिख लेता हूँ इस चीज को. For example, if I have to define Dirac of x, Dirac of sin x. So first find where your sin x becomes 0. First write where sin x becomes 0. It becomes 0 for all k pi's where k belongs to z, and this will be one thing. Okay, is that clear? Now try to write it in this fashion which I've already written. So Dirac of sin of x will be equals to sums k over z, Dirac of x minus k pi divided by cos k pi ka modulus, because the derivative of sin is cos, and cos at k pi would either give you +1 or -1. So cos k pi can be either +1, -1 depending upon k. So this will be -1 raised to power k. And you just take a mod out of it. So cos k pi would be -1 raised to power k, and just take a mod of it. If you take a mod of it, this will be 1. So this will give you summation Dirac of x minus of k pi. Is that clear to you? Now, instead of all this thing, I can write this entire thing. So I'll keep summation k belongs to z minus, you can take it inside also, no worries about it. In fact, I'll take it inside only so that it does not bother you. Dx, now you have e की power minus modulus of x, and then you have sums k belongs to z, Dirac of x minus k. Is that clear? Now, what I would do is, I would try to एक दो चीज में तुम्हें बताने की कोशिश करता हूं, then you will be able to understand. So if just थोड़ा सा इसको expand करके देखो, what is happening? Minus infinite to infinite. This is Dirac of x e की power minus modulus of x. Then this will be, just try to write k equal to 0. So this will be, I'll write somewhere here, Dirac of x, then plus Dirac of x minus pi, then plus Dirac of x minus 2 pi, then plus Dirac of x minus 3 pi, then plus, and then so on and so forth. And if you write here Dirac of x plus pi, then you have plus Dirac of x plus 2 pi, then you have Dirac of x plus 3 pi, so on and so forth. Okay. Are you getting my point? ये चीज समझ में आई? So overall, what you are getting, we are getting minus infinite to infinite. इसको dx को बाद पीछे लिख देते हैं. E की power minus modulus of x, Dirac of x plus 3 pi dx. Then you have plus minus infinite to plus infinite, Dirac of minus modulus of x, sorry, e की power minus modulus of x, Dirac of x plus 2 pi dx. And all these things, integral minus infinite to plus infinite, Dirac of e की power minus modulus of x, Dirac of x minus 3 pi, and this will be an infinite series from here, this will be an infinite series from here. Is that clear? Now, understand my point. ये चीज क्या कह रही है? That Dirac is stationed at x equal to minus 3 pi. So all you have to do is, Dirac when multiplied with a well-behaved function which is e की power minus x, this will give you e की power minus 3 pi का mod, then e की, because minus 3 pi का mod लो चाहे plus 3 pi का mod लो, it is one and the same. क्योंकि mod है, after all it will give you minus like 3 pi का mod. Right? This will be okay. Is that clear? So basically what you are doing, basically it turns out that all this thing is in a geometric series, isn't it? So you can clearly see this is, if you just keep this as 1, so I'll write 1 plus k belongs to z, not z, even n I would write, e की power minus of n pi का mod, and all this multiplied 2 times, because you see here this is 1, again 1, this again, this again. So they basically here they are doubling of these terms. This isko chhod ke all these terms are getting twice. I mean, are you getting my point? If this is 1, you see all the other terms are simply occurring twice. Is that clear to you? Is that clear to you?
Yes, sir.
Okay. So I can write 1 plus 2 times. You just try to find the what it will be. So basically, यहाँ mod लेने का कोई मतलब नहीं बनता है, because you can see that whether you write x is equal, like I can see, because n is positive, pi is positive, so you can clearly write e की power minus n pi, and all these terms would give you. So I would write this. So I'll write a formula here. So if I have this, if I have to sum my geometric series, a plus ar square dash 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 arn. In the limiting case, this will be a upon 1 minus r, where mod r is less than 1. So if I have to write this, then it will be equals to what? So just find the first term. So first term is e की power minus pi, if I'm not wrong, divided by 1 minus of r. What is r? The first term is e की power minus pi. The next term is e की power minus 2 pi. The next term is e की power minus 3 pi. You just divide second term divided by first term. So what you will get? You will simply get e की power minus pi only. Is that clear? And overall, this will give you 1 minus e की power minus pi plus 2 times e की power minus pi divided by 1 minus e की power minus. Is that clear? So I have added 1 plus something. Okay. So it will give you, I think, e की power. Uh, 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 it will give you e की power minus pi plus 1 divided by 1 minus e की power minus. Is that clear? So I can write 1 plus e की power minus pi divided by 1 minus e की power minus. Is that clear to you? And just try to simplify this expression. You can, I think, multiply with e की power pi by 2 both on numerator and denominator. It will become e की power pi by 2 minus e की power minus pi by 2. And you divide e की power pi by 2 below also. So this will be e की power pi by 2 minus e की power minus pi. So this is sine hyperbolic. This is cos hyperbolic pi by 2. So this is sine hyperbolic pi by 2. Below you can see this is cos hyperbolic pi by 2. So overall it will be cot hyperbolic pi by 2. Is that clear? So this integral which I have written here can be written as cot hyperbolic pi by 2. Is that clear to you? Is that clear to you?
Yes, sir. Yes.
Okay. Now, this is a kind of a function that I've given to you. Try to write, try to find this Dirac of sin x minus cosine x. How can it be written? How can it be written? Sin x minus cosine x, Dirac of sin x minus cosine x, how you can write that particular thing? So if I have to write Dirac of sin x minus cosine x, again, this is a function. Just first find where it will be 0. So when sin x is equal to cosine x means where tan x equal to 1 and tan x equal to 1 implies x should be equal to n pi plus pi by 4. Understand my point that you just find tan inverse 1, that is pi by 4, and the periodicity of tan is pi. So pi tan repeat itself after pi in the period as pi. So n pi plus pi by 4 will be the generalized solution to this particular thing. Is that clear? So tan x equal to 1, the general solution would be given by n pi plus pi 4, standard 11 trigonometry. Tan x is a periodic function with a period pi. So in general, the answer would be n pi plus pi 4. Particular solution would no doubt be pi by 4, but generalized solution would be n pi plus pi 4. Is that clear to you?
Yes.
Okay. So now so instead of sin x minus cosine x, I can write that this is your gx. This will be sums all those i's. You can say I can write n, in fact. N belongs to z. This is Dirac of x minus n pi minus pi by 4. Is that clear? Instead of xi's, I have written n pi plus pi 4. So x minus xi divided by the derivative of this. The derivative is क्या आएगा? Cosine x plus sin x का mod at x equals to n pi plus pi. Is that clear? So cos of n pi
Yes.
plus pi by 4 will be equals to what? So you just take n is equal to 1. So n equal to 1 means pi plus pi 4. N equal to 2. So if you see that either you will be in the third quadrant, either you will be in the first quadrant. देखो अगर n की जगह 1 लोगे तो pi plus pi 4 sin pi plus pi by 4 भी नेगेटिव होगा -1 upon √2 एंड cos pi by 4 भी cos pi plus pi by 4 भी क्या होगा -1 upon, और 2 pi plus pi by 4 करोगे तो sin भी पॉजिटिव cos भी पॉजिटिव. इन एनी केस ये दोनों 1 plus 1 by √2 plus 1 by √2 आएंगे. Is that clear? So 1 by √2 plus 1 by √2 ही आएंगे. Is that clear? This will remain 1 by √2 plus 1 by √2 or minus 1 by √2 minus 1 by √2. In any case, this will remain 1 by √2 plus 1 by √2 if you take a modulus out of it. So this will be 2 upon √2, that is √2. So 1 upon √2 sums n belongs to z, Dirac of x minus n pi minus pi. Is that clear to you? So instead of writing Dirac of sin x minus cosine x, you can as well represent it in sums of all these Dirac delta functions having spikes at pi by 4. Is that clear to you? Is that clear to you? Or isn't it clear? बोले ये नहीं समझ पा रहे.
Yes, sir. Clear.
Okay. Now, again, coming back to another thing that we've skipped or somewhere, write it. So let us come back to the three-dimensional representation of Dirac Delta function. So let us come to the three-dimensional representation to Dirac Delta function. And as I write it, before that, let us take a physical insight to a vector field. So let us take a physical insight to a vector field. So let us take a physical insight, and थोड़ा सा you should be knowing about divergence. अगर नहीं भी पता हो तो I'll write it, don't worry. Okay, so I'll write the formula of divergence, the radial formula of divergence. I'll write, don't worry about it. But overall, try to focus your attention on try to focus on this particular what you can say this particular vector field. This is r cap over r square. Is that clear? So if I'm saying r cap upon r square, so if v vector is given by r cap upon r square, then you can clearly see that this particular function, this particular vector field suggests that this is a vector field which is dying out as you are going as r tends to infinity. So if I have to make a pictorial representation, so as my r decreases increases to infinity, my vector field strength would decrease. But overall, this is a radially outwards vector field. Is that clear? So this is a radially outwards vector field. Because you can see this is r cap, and multiplied with r cap, you have an r 1 upon r square, and 1 upon r square is positive. 1 upon r square is positive. 1 upon r square is positive, and if you are finding r cap upon r square, so what does it mean? You are actually moving in radially outward direction. No doubt the strength of field would decrease as r tends to infinity. That is absolutely fine. But overall, this is a radially outwards vector field. Is that clear? So this is the radially outward vector field. Is that clear to you?
Yes.
Okay. Now, what do you expect? The divergence that you expect out of this should be a positive one, because divergence quantifies the spread of the wave, the spread of the vector, isn't it? Divergence physically, what does it mean? So, for example, if I say the divergence of electric field would give you an idea of the charge distribution in the space. So basically, it says how your vector field, how your electric field is spread. You take a divergence out of it, so it will give you an idea as to how your charge distribution is there in the space, isn't it? So this is your celebrated Gauss theorem, isn't it? Maxwell's first law. So overall, try to understand, if I want to write the divergence of a vector field, what does it imply? It implies how your vector field is spread in the space, or your vector field spreads, or you can say diverges in this, diverges or converges if it is a negative vector field, how your vector field diverges or spreads out. Is that clear? Now, as I take a divergence out of it, if you're aware, the divergence formula, the radial part of divergence is equals to 1 upon r square del by del r of r square VR. If you are not aware, just remember this formula. This is the divergence of a vector field, the radial part. I'm not writing the other parts, it's the radial part, because the vector field is only a radial function. So I'm not interested in other things, but overall this would wait. So if you just try to find the divergence of r cap, what you will find? The divergence of r cap, divergence of v vector would be 1 over r square, then del by del r of, I think, r square into 1 over r square, then it will be this, and that will be 0. Surprisingly, what you expected doesn't come out here. So you expected that this is a vector positively, or radially outwards vector field, which suggests that this divergence value should come as some positive value. But in fact, you found that this particular value is 0. And this is certainly, like, you cannot expect this kind of thing, because you clearly know that this is a vector field. It is having some finite value as it spreads out. So there should be some divergence. I mean, there should be some non-zero divergence. But here you find that the divergence is 0. And certainly there is nothing wrong with this formula. This is quite established formulas. These are not those formulas which you can think that this is wrong. So there is something that we are wrong. Okay. The second thing is, let us understand if you have a theorem which says, okay, you have a theorem. Let's say if I have a vector field v vector, and instead of finding the divergence, what I would do is I would try to I will try to I will try to encircle it in a spherical region of radius r. So I will try to encircle this in spherical region of radius r. Is that clear? So if I encircle my vector field in the spherical region of radius r, what I would get? I would simply write, if I want to write the flux of it. So VdA, V vector dot ds vector would be equals to what? Integral. What will be the vector field here? Vector field will be equals to 1 upon r square r cap. Is that clear to you? So if I write on the surface of the sphere, the vector field will be 1 upon capital R square r cap dot. If you don't remember it, just for right now, just remember this differential element area. We'll do all these things electrostatics also. Can be written as, I think, sine theta, r square sine theta d theta d phi r cap. So for right now, if you're not aware, just remember this thing, that this patch of a small differential area element would be r square sine theta d theta d phi r cap. So this will be r square sine theta d phi r cap. So I'm just trying to find the flux enclosed by this vector field in a spherical region of radius capital R. So what you will find, this r square gets cancelled. Overall, this will become, I think, 4 pi. So I don't think this is a difficult integral. D phi integrated over all to, 0 to 2 pi, and sine theta integrated from 0 to pi would give you 2 into 2 pi, that is 4 pi. So overall, you're finding that the flux enclosed is 4 pi. And there is a theorem. There is a theorem called as Gauss divergence theorem, which says that this integral, this surface integral, is equals to del dot v vector d tau. So basically, what volume it encloses, you just take this surface encloses what volume. Over that volume, if you try to take del dot v vector d tau, it should be equal to v vector dot ds enclosed by this surface. Basically, the flux coming out of this surface should be equal to del dot v vector d tau. But del dot v vector d tau is 0. You can see. So del dot v vector is 0. You've written it here. And if I'm writing, if I'm integrating it on constant limits, so it will not even be an arbitrary constant. So answer would be 0 in fact. So what I want to suggest is that if you want to write an integral 0 dx, then you can simply say this is c. But if I say integrate 0 from 1 to 2, then the answer would be 0 into 2 minus 1. So this will be 0. So I'm integrating on limits that I know. Basically, I'm integrating on constant limits. This is 0. So this overall would give you a 0. But on the left hand side, you have this 4 pi. So you are encountering an ambiguity that needs to be resolved. Obviously, this particular theorem cannot be wrong. I mean, this particular theorem has got, this is quite mathematically intact theorem. So here you are not wrong. So where you are wrong, you have to find it. Is that clear to you till now? Is that clear to you? Okay. So,
clear, sir.
Okay. So where does this lacuna, I mean, where does this this problem or ambiguity arises from? So where does this ambiguity arise? So this ambiguity arises because of the derivative function. So basically, when you were extracting the divergence, you were writing this particular thing, that is 1 over r square del by del r of r square del, I mean, this was VR. The root cause of this problem is this particular function, this particular derivative can only be defined if r is not equal to 0. So what does this suggest? This suggests me that del dot v vector, whatever I'm evaluating it for all points which are not equal to 0. So basically, I'm evaluating this particular derivative for all r not equal to 0. Is that clear to you? What about r equal to 0? And certainly you can see that r equal to 0, I cannot write. I mean, I cannot write. So again, this is a problem. This is a problem where at r equal to 0, I cannot write my function. So this is not behaving right at r equal to 0. It will be a not defined function given our elementary calculus background. Given our elementary calculus background, I cannot write r equal to 0. What would be it? But what does this exercise suggest me? That del dot v vector is 0 for all r not equal to 0. And if I am writing a flux from this particular vector field, I'm getting 4 pi. What does it imply? That del dot v vector d tau must be equal to 4 pi, isn't it? It cannot be 0. It has to be 4 pi. And if it has to be 4 pi, there is a certain contribution which is coming from the origin, because del dot v vector is 0 for all r not equal to 0. So therefore, this entire integral value that I'm getting, which must be equal to 4 pi, must be coming from the origin itself, where you can see that your function is not defined. So for such functions where you have a singularity at r equal to 0, at this particular singularity, you cannot define your function in a well-behaved manner. This particular thing can be encapsulated in the form of three-dimensional Dirac Delta function. So understand, again, there is a need to write a distribution, and you have to say certainly that the entire distribution or entire contribution to this integral is coming from r equal to 0. Is that clear to you? And this particular thing can be circumvented by the help of what you call as Dirac Delta function in 3 dimensions.
Three-dimensional Dirac Delta.
Okay, is that clear to you? So what I would write, I would say that del dot r cap upon r square would be not equal to 0. Rather, it will be equals to 4 pi Dirac of this. Why I would write this way? Because you can see that for all r not equal to 0, it should be equal to 0. Fine. But at r equal to 0, there is a certain contribution. And that certain contribution, if I'm evaluating it from the surface integral side, I'm getting a 4 pi. So in order to write this, I've multiplied it with a constant. The properties remain the same. So properties remain the same. So you know that integral from minus infinite to plus infinite, fx Dirac of x minus x naught in single integrals. I mean, in a single value, in one variable integral gives you fx naught. Similarly, if I want to integrate over volume, my Dirac cube r vector d tau should give me 1. And similarly, if instead of this, I have a function at r equals to r naught, if I have a function fr, and if I have a Dirac r vector minus r naught vector over entire volume or entire space, this should give me f of r naught. So now let us try to resolve the ambiguity that we were confronted upon by the previous thing. So previously we were trying to find del dot v vector for this particular v vector, which was given by r cap upon r square. And we fairly resolved this problem by saying that possibly this should be equal to 4 pi Dirac cube r vector. Let us see, does that resolve our problem? So now let us try to find again that what will be the flux enclosed by v vectors. Flux enclosed by v vector given by r cap upon r square. This will be equals to flux enclosed in a sphere of radius r would eventually again be equals to the same thing. So it's not changing. It will be again same 4 pi only. You just try to find it, you'll get 4 pi only. But what about the integral del dot v vector d tau? Now it will be equals to integral del dot v vector would be equals to what? 4 pi Dirac cube r d tau over entire volume. And if on entire volume I am writing this, what it will be equals to? This will be equals to 4 pi integrated three-dimensional this Dirac delta function d tau. This will be equals to 1. I have already written it here. This will be equals to 1. So overall it will be 4 pi. So here we have resolved our problem. So you can understand fairly enough that wherever your problem with regards to point mass, point charge would come, you will always find such Dirac delta functions. So the moral of the story is, the first thing is Dirac delta function to me as a first exposure would come in electrostatics mostly, or possibly in gravitation, or possibly in impulse kind of thing, where you have to model. So Dirac delta function would naturally appear you can say where you have to model the point charge density and all those, point mass density, point charge density, and all those stuff. Is that clear to you? Now, in fact, one would ask that if this is the case, what it will be for different other coordinate systems. So for example, if I'm writing the Cartesian system, what if I'm writing in different other systems? So here I'm just jotting down the formula, you just remember them. Okay, we can obviously derive them, but it would be better if you just remember them, because otherwise there would be too many derivations. Although the derivation source is simply that only Dirac of gx, that only makes the source of the all these things, but still instead of instead of writing three-dimensional Dirac delta function delta x, delta y, delta z, so this will be Dirac delta representation in Cartesian coordinate. Is that clear? So instead of Dirac cube r, you can write Dirac x, Dirac y, Dirac z. Instead, if you have some r comma theta polar representation, then you will get 1 over r Dirac of, and if you are saying that I'm writing my Dirac delta function at r vector minus r dash vector. So basically, I'm stationing it at r dash. Then what it will be equals to? And let's say this particular point is r dash, and let's say this is theta dash. Okay, then it will be 1 over r Dirac of r vector minus r dash vector, Dirac of theta minus theta dash. So this will be your, if I'm writing in 2 dimensions. Okay, is that clear to you? If I'm writing in 3 dimensions, for example, instead of 2 dimension, if I have 3 dimension, and let's say if I am in a, let's say a cylindrical coordinate system, all these things will do as we move ahead. But overall, I believe that all these things thoda thoda to aata hi hoga. That is why I'm taking this liberty. If you are in a cylindrical coordinate system, then the scaling would be done by 1 over r Dirac of r vector minus r dash vector, Dirac of phi vector minus phi dash vector, Dirac of z vector minus z dash. If you are not aware, you can skip this particular thing also. We'll do it all over again in this electrostatics also. But overall, if you can just jot these formulas down, it would be good for you. So Dirac r cube r vector minus r dash vector in spherical polar coordinate system 1 upon r square sine theta, Dirac of r vector minus r dash vector, then Dirac of theta vector, sorry, not theta vector, theta, and then this you have this phi minus phi dash. Is that clear to you? I'm not this.
Yes.
Pictorially, I've already written here. I've divided these. I mean, so basically, vector has been replaced. R vector has been replaced by the this. So instead of writing r dash vector, I'm writing the polar coordinates of that point, r dash and theta dash. Basically, I've removed all these things. This is how you will write in 3 dimensions. Okay. So overall, just try to remember these terms. So if I have to write in different other coordinate system, this would be it. Is that clear to you? Okay. Okay. Let us do a few more things and conclude our lecture. Okay. So if I have to find, the another thing that is there, like for example, if I have to find what will be the derivative of, what will be the derivative of theta function, where theta is unit step function. How would you do? I'm giving you 2 minutes, just try to find it because then our class will be over. If I have to find the derivative of theta function, where theta is a unit step function. So this is unit step function. You can say Heaviside function. In older literature, you will find this as Heaviside function. Okay. If you have to write the derivative of unit step function, and that unit step function is what? This is, as the name suggests, there is a step of unity. So if I'm writing x greater than 0, this is 1. If I'm writing x less than equal to 0, this is 0. And if I want to write d by dx of theta x, then what would be it? What would be it? Obviously, in ordinary calculus, if you want to write, it cannot be the case, because in ordinary calculus, you can see that x equal to 0, your function is discontinuous. And a function which is discontinuous at a point is non-differentiable at that particular point in ordinary calculus, whatever we know for ordinary calculus. But in distributional sense, like for distributions, we can still define a distributional derivative. So just want to know, try to find the derivative of d by dx theta x. I'm giving you a single minute. अगर समझ में आता है तो ठीक, नहीं आता तो I'll do it. Don't worry. But just spend a minute over it. Just try to sketch it and just try to understand ki who kya raha. Okay, so let me do this particular thing. So अच्छा एक और चीज समझा देता हूँ. Whenever you are told to ask, whenever you are asked some properties regarding Dirac delta function, try to use integration. Try to use integration. This is a kind of whatever you say in your language tips and tricks or whatever. So if at all, if you write an integral involving Dirac delta function, and let's say this is your Dirac expression on the left hand side, and this is your Dirac expression on the right hand side. And if you somehow equate these two integrals, then your expression on the left hand side involving Dirac delta function, and this would be equal. So this is a kind of thing that you can most possibly do. So whenever you are doing this kind of thing, just use a test function. Just use a test function and try to find an integral involving this. So basically, I should have written it. This is Dirac delta function. So let us see how. So if you just try to find d by dx theta x, just try to multiply it with f. Okay, just try to multiply it with f, and I'm integrating it from minus infinity to plus infinity dx. So just do integral by parts. This will be fx into theta x from minus infinity to plus infinity. And this will be minus integration from minus infinity to plus infinity. This will be, I think, df by dx. And then you have d theta. I think d theta by dx का integral will be theta x. Is that clear? Is that clear to you? I don't think there is a problem till now. Okay. Now you can see as x tends to minus infinity, your theta x would tend to 0. So the lower part, whenever you place, this will be 0. So overall it will be 0. But the upper part will be somewhere this. Okay. And this will be what? You can clearly see here also your theta x is 0 for all x less than 0. So why not integrate it from 0 to infinity? F df by dx into theta x, and theta x will become 1 dx. So what it will become? It will become limit x tends to infinity f of x minus, this will be df upon dx integral. So this will again become limit x tends to infinity f of x minus f of 0. So overall, you can write this as this integral, these two limiting case will become 0, and you will get an f of 0 on the right hand side. So what you're writing, you can write that d by dx of theta x is equals to what? Is equals to f of 0, and instead of f of 0, sorry, this thing, sorry, my mistake. Minus infinity to infinite f of x d theta by dx dx is equals to f of 0, and instead of f of 0, you can write minus infinity to infinite f of x Dirac delta x dx. Now you can equate these two terms, and you can clearly find out that d by dx of theta x is equals to Dirac x. Is that clear? So the derivative of unit step function is Dirac of x. Now just try to solve a problem. We'll solve it separately also. Now try to find me d by dx of greatest integer function. This is a homework to you, and we shall meet tomorrow. This was Arjun Taylor.
भैया वॉइस ही ब्रेक हो रही है लास्ट पूरे क्वेश्चन में.
Okay, so कुछ नहीं हो सकता because the lecture is about to close. So I'll repeat it all over again tomorrow.
हाँ हाँ right.